Okay, this is going to be our third video in our DC circuits series. I think this is going to be a short video. This video is going to be talking about content from section 26.3 of the text, which is electrical measuring instruments. There's only a couple of topics that I want to touch on really briefly here. We'll do a couple of quick examples and then move on to the next video. Okay, so in the text, the text goes into some more detail about some of these things than we're really going to be interested in here. So it starts off by talking about these galvanometers. Basically, it's like a maybe I can scroll down to show you a picture here a little bit. Oh, have I left additional content here? I have. Okay. Anyway, we won't need some of those bottom pages. I still have some of the previous slides on there, but that's fine. So let me scroll down to here. Basically this galvanometer is basically like a resistor that as current flows through it, and the text goes into some more detail here and has some more drawings about it. But basically, as this thing has current flowing through it, it pushes the needle in such a way that it's going to indicate something on your dial here. Okay, so the text talks about this a fair bit. But we're just going to talk about them in the context of ammeters and voltmeters, and we will we're going to kind of skip over some of the other stuff. Okay, so let's get right into ammeters right away. So an ammeter is a meter that's going to measure the current passing through it, right? So an ideal ammeter would have zero resistance, so that including it in any circuit would have no effect on that circuit's current, right? So we would like it to have zero resistance, but real ammeters obviously are going to have some small finite resistance. Small is the goal here. We want it to be small in comparison to the things that we're measuring in the circuit, so it's not significantly impacting our measurements, right? We can take an ammeter that isn't set up to measure large currents, and we can adjust it so that it can measure larger currents, and we would do this by hooking up resistors in parallel with our meter, so that current can bypass the meter, and we can sort of tell what the current, the small portion of the current going through to our needle really is, right? And this resistor that we would hook up in parallel is what we would call a shunt resistor. Okay, so here we have a little discussion and an equation here. So equation 1. So for some internal current, IFS, which makes our ammeter read its maximum value on the dial, and let me just pause here to say that IFS is meant to stand for I full scale, and that means whatever current it is that when passing through the ammeter would make the needle on the dial point all the way to the maximum reading. Okay, so IFS is that value. So what we're saying here is that for IFS, which makes our ammeter read its maximum value on the dial, and a coil which moves that dial of resistance RC. So that would mean that this little setup here, which is kind of like a dial, but you can also think of this just as a resistor with RC in a sense. Okay, so for a resistor with that RC, we need some shunt resistance RSH, given by the expression that we see here, where IA is the total incoming current. So we can imagine that there would be some IA coming in here, not just the I that we have written here, but IA. So we have a different labeling scheme, and it's going to read this IA as the maximum deflection here on this dial. Okay, and so what are we doing here? Sort of, we have our ammeter set up. Let's say we just had this upper part of the ammeter set up. Okay, so just this stuff up here. It can only read stuff that deflects this dial to a maximum of over to here, right? All the way to the right. So it'll read 0 on the left, and as the dial deflects all the way to the right, it's going to read its maximum reading. But let's say that we're trying to measure a current higher than that. This is what we're talking about here. We can include this shunt resistor down below, which is going to take a bunch of the current and have it flow over the shunt resistor, so that so that our RC works out just right, so that the amount that we want to measure coming in, this IA, is actually somewhere on, or actually gives us a maximum deflection on our dial here. Where if we didn't have this shunt resistor, it would be the pointer would be pushing all the way to the maximum, but it would really be more, and it would want to be further to the right, but it's actually just floored. It's just pinned, so it can't go any higher. Okay, so let's take a look at an example of how we would set up one of these ammeters, and sort of what the calculation would look like, right? So we have this example here. What is the shunt resistance, or what shunt resistance is required to make a 1 milliamp, or I should say, sorry, that's not a milliamp, that's a microamp, with a 20 ohm ammeter into an ammeter with a range from 0 to 50 microamps. Okay, so that's the question. I have numbers worked out for this over here, and so maybe let me redraw the setup here, and we can kind of look at what the whole setup looks like. Okay, so we can imagine this is our ammeter here, and I'm going to probably do a pretty terrible job of drawing this, but we'll try. So this is our little internal resistor attached to our needle. This is our scale up top. We would have a bunch of markings here, and we'd have some position for our needle, right? We would have some wires going up to this setup. This thing would have a resistance RC. This thing's going to come down to some positive and some negative terminals here. We're going to have some current coming in. This is going to be IA, and we're going to have some current going out, right? Now, this is what it would look like if we had no shunt resistor, right? And so the only resistance involved here is RC, but we know that our RC is not sufficient to give us what we need here. So we need to add in a shunt resistor to get some of the current flowing down in the direction of the shunt resistor, so that we can get the correct measurement, so that IA basically pins our reading on the right here. Okay, so we're going to end up with some shunt resistor in here. We're going to call this R shunt. And so what have we kind of set up here? Well, we're going to, first of all, we're going to label the current that actually goes up this way. This is going to be IFS. This is I full scale. Okay, so we need exactly I full scale. We need exactly the current coming up here that's going to push our needle to exactly this full scale reading on the right. Okay, and so we need enough of IA to be bled off down our shunt, so that it's not going through our needle here, right? And so if we kind of think about this setup here, what do we really have? Well, what we've really set up is something that looks like this, right? We have a setup that looks like this now. Okay, and so we can think of this as our RSH, this as our RC. We have some IA coming in here, and we know that going this way, we have some IFS. So what's going to be going this way? What's going to be coming through? What's going to be coming through here to RSH? Well, that's clearly going to have to end up being IA minus IFS, right? Because we have, and this is again just Kirchhoff's sort of setup here with junctions, his junction rule. We have current coming in. We know that we're going to have some amount of current going out. We have some of that current going this way, so the rest of it has to go this way, right? And so this is the setup that we want. We also know that our potential between A and B here, well, that's going to be the potential across RC, and it's also going to be the potential across RSH. So if we think about it like that, and we think about well, what's VAB equal to? Well, VAB is equal to IFS times RC, right? It's going to be, this is basically just V equals IR. It's going to tell us that VAB is equal to IFS times RC, so across this upper branch, but across the lower branch it's also going to be equal to IA minus IFS times RSH, right? And so this is the sort of formula that we're given above, here, to describe what, well, how these two resistances are going to relate to each other. And so now, using this formula that we sort of derived here, we can just substitute in the numbers that were given in the problem, right? And so we're told that we have a our meter here can read 1 microamp, and it's going to it has a resistance. So our RC here, this is like our RC. This is our I full scale, and this is our IA. Okay, so we want when we connect this 50 microamp. Did I just say micro again? Anyway, when we connect this amperage to IA, when we basically have it connected to this positive terminal, we want to see this thing get pushed all the way to its full scale reading. Okay, and so we just need to substitute in the values that we have above for this here, and if we do that, basically we're trying to solve for RSH. So we're going to end up with an equation that's RSH equals I full scale times RC divided by IA minus IFS. Okay, and so this is the equation that we're going to use. We know what IFS is, we know what RC is, we know what IA we want to give us that full scale reading, and so we can substitute in these numbers. This is going to end up being RSH is equal to well, IFS. Our IFS is 10 to the negative 3. We're going to have RC, which is 20 ohms, over IA, which is going to be 50 times 10 to the negative 3. And we're going to have, again, an IFS of 10 to the negative 3. Right? So if you do that calculation, clean the whole thing up, you're going to end up finding that RSH is equal to 0.408 ohms, and that's terrible, like that. There we go. Okay, so this is the resistance that we would need to insert into our ammeter here, so that when we have an incoming current, an IA of the value that we want here, that we're going to end up with a reading of a full reading on our meter. Okay, and so we can oftentimes, maybe you guys have used these in the lab. I think you guys still use those yellow ammeters that we have in the lab. You kind of have to switch depending on which sort of scale of resistance you're looking at. You switch it, and so you're really switching out these shunt resistors, and so now you can actually get the reading for the appropriate sort of range of currents that you're looking for. Okay, so those are amp meters, just very quickly. I don't use them very often here, and so I mean, we might see these in some problems. It's important to know how they work, but you probably won't use this calculation too much outside of a lab. When you're trying to figure out, what you need to have your amp meter set up, so that it'll give you the readings that you want. I'm going to move on here to voltmeters. So a voltmeter measures the voltage, or the potential difference between 2 points. A perfect voltmeter would have infinite resistance, right? So if we had a perfect voltmeter, we wouldn't be drawing any current across it. We would just want to be detecting what the potential difference between the two ends that we connect to our circuit, right? So let's say this was our voltmeter. We would want to connect to this point here, which would be at some potential VA, and some point here that would be a potential VB, and we would want to know what that difference across this circuit element, or what VAB is, right? And so in the same way that we can modify our amp meter, we can modify our voltmeter, right? We can change, and this is the setup that we have here. So we still have the same RC, and we still have the same current sort of required to push our RC in such a way that the meter reads something on our dial here. But now we have it hooked up in series, not in parallel, with RS. RS is an additional sort of resistance that we put in series with our coil that allows us to read different scale voltages, right? So we have to choose the appropriate RS so that our scale falls within the range of what we're actually trying to measure. Okay, and the way we do that is using the expression that we see here. This is again just another statement of V equals IR. This is the voltage that we want to read full scale. So this is the voltage that we want to give us a full reading over here. I full scale is exactly what we talked about above, the current required to push our RC resistor in such a way that the dial points to its maximum amount. And this is just the total of the two resistances, RS and RC, right? And this is just V equals I, and R is just the total of these two R's, okay? So let's take a look at another example with this pretty simple example. We are going to be dealing with the same setup we had above, so the same dial that we had above, so same characteristics here, but now we want it to have a range when we have it set up as a voltmeter, so not a resistor in parallel, but a resistor in series. When we have it set up as this voltmeter, we want to be able to read between 0 and 10 volts. Okay, so I think I have some of those numbers here. Yeah, it's right over here. And so I won't bother redrawing the setup here. We basically have the same idea here. We basically have this, okay? And so we'll just do it down below. This image is from the textbook, so if you want to have it side by side while we're doing the problem, you could pull that up. But basically we know that as I said above, V equals IR gives us this expression that VV is equal to I full scale times RC plus RS. Okay, and we're looking for the RS, this additional resistance that we need to stick into our internal circuitry here of the voltmeter so that it can read up to 10 volts. Okay. And so for a step we want to solve for RS. That's simple enough. RS is just going to be equal to VV over IFS minus RC, right? And at this point we can pretty much just substitute in values and solve. We want a VV possible reading of 10 volts. We know that IFS is actually 0.001 amps, right? And RC is the resistance of our dial, so our resistance there hasn't changed. That's going to be 20 ohms. And so if you do this calculation, you're going to end up finding that you need an RS equal to 9,980 ohms to get a full scale reading on your voltmeter of 10 volts. Okay, so if you were to hook this up to something that you know had a 9-volt potential difference, you'd get 90% of your meter. That would be a pretty good meter. You've set it up correctly. You have the right RS in there. Okay. So those are basically amp meters and voltmeters, sort of in a really brief nutshell. That's really all we need to know about them to be able to make good use of them. The textbook goes on to talk about ammeters and voltmeters in combination. I mean, it's important to note that as you use these things, so often you're going to want to know more than one thing about your circuit that you've set up, right? So you're going to want to measure things like the current, the potential difference. If you measure these in conjunction, there's a bit of an issue, right? Because if you're measuring current, well, depending on how you set it up, either your current measurement is going to have a significant impact on your potential difference measurement, or your potential difference measurement is going to have an impact on your current measurement. So depending on how you set those up, they're going to have some impact. The goal would usually be to have these things have small enough or large enough resistances that they have very little impact on the actual measurement, and in that case you're fine, right? So you always want to be aware that the act of taking the measurement when you're working with these circuits has some impact on it, right? And you want to try to minimize that impact. But yeah, so that's one thing to note. Additionally, we've only really talked about measuring I and V, right? We've talked about measuring current and potential difference. but from I and V using V equals IR or our expression for power, P equals IV, right? We can get at R and P quite easily, right? We can just mix and match these two measurements and find R and P quite easily. The textbook goes on to talk about other meters in addition to ammeters and voltmeters. It talks about ohm meters and potentiometers, which are two other meters. We're not really going to talk about those here. We're not going to need them too much for the course. It's important to know that there are other things going on. You can kind of see them in the textbook and give it a read. But generally speaking, you're going to use ammeters and voltmeters, and that should pretty much cover most of what you need to be working with. Okay, so we'll end this video here. It's a short one, and we'll pick it up in the next one. You guys might notice that there's additional slides below here, but these are just slides from the previous talk that I haven't deleted out of this PDF yet. Okay, so we'll leave it here, and I will see you guys in the next one.